escucha ahora?
Trends in DCI Interconnection. Can you hear me well? So thank you. Thank you for those who survived yesterday's night. We had an internal bet to see if we had more than 10 people in the audience this morning. There's more of 10 of us, so that is great. Let's see if we can solve the speaker issue.
Okay.
Okay. My name is Gonzalo Sosa. I work at Nokia. I am the business development manager, the optical business development management. I'm in charge of Latin America and the Caribbean. And the idea is to look at trends in the DCI market, particularly around interconnection. If we look at the analysts' forecasts for the market in Latin America, we still see a growth or a growing trend towards 2029, accumulated 2% annually. And another trend that analysts show is that not only the metro market will grow, the very traditional DWDM, but also its weight. Both trends are upwards. Another thing that we can identify, if we look at, well, today, if we look at 2024, the speed online also shows an upward trend. Line speed will increase in the next couple years, 100 gigabits, 200. That trend will reduce and the speed line will increase, and we will reach speeds of like 800 giga, 1.2, 1.6 terabit as the more standard line speeds. At Nokia, we have a division that is called Nokia Bell Labs. And Nokia Bell Labs, in addition to studying technology and looking at what will be the next technology in the upcoming years, what they do is study the new market trends, particularly the impact AI will have online. The study that they published this year is available. You can download it from Nokia's website. And it will basically study the growth of AI and the AI traffic, and how that traffic will impact networks. What is promoting the growth of these networks is what we know as cloud IT. There are more and more companies using cloud services. Also, end users use cloud services, and these services or mobile applications. We all have a mobile phone, we all have video apps, even work stuff on our phones. We use our mobile phone in different arenas, sporting events. Even when you are at the stadium, we could be looking at the repetition of a play, whether there was a foul, whether it was offside, and so on. So all video apps that are still growing, and video apps that cannot even be recognized by the human eye. For example, 8K applications. The human eye does not distinguish it, but it has applications, for example, for the recognition of patterns. I can see if there are flaws or not in a product before it's sent to production. So the industry is currently using all of this. And the new trend, of course, around everything AI related. There's a massive growth, especially in the hyperscaler world. They're building data centers that go well beyond what we can imagine. Racks supporting 80 kilowatts, completely crazy. And the traffic that uh, is sent to our networks. By 2033, traffic is estimated to reach, in a moderate growth, reach 3,000 hexabyte a month globally. We're always discussing global numbers here. And what is interesting in this report, and we can see the AI factories, the providers, CSPs, enterprises, and this traffic that is generated, or the growth that is estimated, will impact the biggest bandwidth in the network will be observed in the access network towards end users, whether it's the actual end user at home or businesses. So that will be 31% of traffic that will be covered by these access lines. Another big percentage, that is 28, close to 30% of traffic distribution, will be found in these metro connections from the edge data centers and in metro environments. And the smaller percentage will be observed in regional connections. So, what does that mean for the data center world? What will it be like by 2027? There will be a 100% bandwidth growth promoted by AI. And with regards to the data center, there will be a 27% data center capacity increase, and it will be driven by demand, power, space. And when we have this, is where we will find in this market opportunities for growth. And the uptake systems, there it will increase twofold. It will double by 2027, and that is just 2 years away. Well, this was animated, that slide. I'm not sure why it's not showing, but it doesn't matter. I don't know how many of you are familiar with this. Typically, the first WM systems, we had maybe a 2.5 giga. We moved to that's of 10 giga. It increased fourfold. Then we had the coherent technology going to 100 giga, and we multiplied tenfold system capacity. Technology continued to increase and grow, and the capacity from fiber continues to increase. For 2 generations now, well, on the new generations, we cannot really milk it anymore. The end capacity of fiber, or that increase once we have a new technology, is really minimal, maybe less than 10%. Considering this growth, hyperscalers have realized that growth is not just given by technology, but also the amount of fiber I have in the system. And the to speak about some figures, we had 90 gigabytes. If we speak about a pluggable, for a theoretical network, we could have 300 kilometers. And the technology that we have nowadays, 140 gigabytes, we could reach around 6,000 kilometers.
¿no? De 300 kilómetros pasamos a 3000. Antes no se
So in the past, we couldn't have 800 gigabytes. Now we can, and we are speaking at about around 2,000 kilometers. Pluggables have evolved, and there's been a change in the priorities in the businesses that use this type of technology on the ground. There's an increase in the need to reduce power, the power that we use, and reduce the space that is used. And yet, there is a decreasing demand in terms of the additional capacity that that technology can get from fiber, because I have more fiber, particularly in the metro environment, which is very easy to lay fiber. We could have fiber is not necessarily something that is restricting that, like it could be a long haul network or a submarine one. These pluggables also have they have to be highly configurable. They need to be very practical. When I have something in the network, they need to interface with different protocols, and they need to be programmable at different speeds, because a router could have 400, 200, 800. The distance from these routers also needs to be taken into account, and they need to be programmable and easy to implement in my networks. So this was also animated, supposedly. I don't know why it's not showing. But what I was saying, or what that slide shows, is that let's suppose that we have a router where we accept 800 gigabit pluggables. On the other end of the network, we don't yet have routers that support those pluggables, and we could have them at 400 gigabits. So the pluggable that supports it, I will configure it to 400 gigabits so it speaks to the other end. And once I change this router, you don't need to change the technology that you have on this end. You just change the settings or configuration. And yes, of course, you need to have the new router with the new pluggable for 800 gigabits. But it's not necessary to start changing the technology on this end. That's the main concept. I'm sorry that it's not animated, that the slide's not animated. In the optical world, there are several ways of arranging the metro networks. We could have a link, an end-to-end, a set of routers. For example, we could have a 400 gigabit ZR. We could have a WM network end-to-end with a ZR as well, or several ZR pluggables. And if we keep evolving, we could visit a network with ZR plus, larger distances, capacity, depending on the need that I have on my network. I could have a ring for protection, or meshed networks due to the settings of the rings. For example, in Brazil, where there are many networks that fail often, or maybe we have aerial stretches and there are problems with reliability as well. So we'll go to meshed networks. If I go from left to right, it becomes increasingly complex, an increasingly complex network. It means more intelligence, and everything around ZR pluggables. If there's no intelligence or coordination, I won't be able to create a meshed or ringed network. All of this needs a certain coordination, of course, between optical and IP teams. Companies will have people that are knowledgeable about optical technology, and it's managed by that operational group. And then they will have another group in charge of IPs, routers, and switches. In general, those both operational words don't talk to one another, and there's just coordination across the capacities that are needed and the type of services that I have to deliver.
Lo que está
Basically, what is missing here is knowledge of the operational groups. In here, you can do this on an AXP, and when I go to more complex networks, I will have to balance the power. I have to be careful with different types of lambdas that have to coexist in the same network. We have to have certain caution so as not to affect the traffic. As regards the current deployments have the classical router on one end. They're black and white. They're not colored. They are connected to the transponders. The transponders convert the signals to a higher rate, to a higher speed, and this is transmitted through the network. This solution basically provides maximum fiber capacity. I can make the most of that fiber. I can also have different types of clients. I can do that aggregation at 100, 400 giga clients or 10 giga clients. In addition to that, in many countries, this is, for example, a point for intercepting things. If this is required by law, I can intercept traffic. Normally, transponders can intercept this traffic and obtain information. Or also, many companies use this classical configuration to comply with certain SLAs. There are multiple clients. Some clients purchased capacity on that type of network, and you have to comply with certain SLAs, otherwise you have to pay penalties of some kind. Quite obviously, this solution in the classical transponder provides all the optical facilities, so I can know the performance, I can know what the status of the network is. Now, what are the negative points of this solution? This is a solution that has the highest power consumption, because this is a consumption of the router, of the pluggables. These are black and white plugs that are connected to the transponder. This is an element that consumes more of the network. It also consumes more space, as a larger footprint and a higher capex. On the other hand, the IPs over DWDM have the advantage that they require lower power. I don't have the transponder part. I am eliminating the entire consumption of the device, the DWDM, the investment, of course, is minimum, the much lower capex. There's a much smaller footprint as well. And additionally, there is optical interoperability. The negative points are the operational complexity, which is what we were explaining in the previous slide. So depending on the type of network, these IP over DWDM networks work well when it's end-to-end or point-to-point, but when I have rings or other types of meshes, the management of these networks is far more complex, and you need to have expertise on the DWDM network, which is quite high. Additionally, a further limitation is that I am limiting the speed to the router port. It's limited to the router port speed. If you only accept 400 giga plugs, I cannot increase the bandwidth. And this, of course, implies that I have spans that are very big. I will have difficulties, and the fiber capacity will be reduced. What we are seeing in the industry is we are using the positive things of the transponder technology and the IP over DWDM. The concept of thin transponder is what is now being considered. This is a lighter transponder that doesn't have that much intelligence. It practically has no intelligence. This is a small box that only accepts inserting plugs. And this will continue to exist. This black and white connection will continue, but the connection to the DWDM will be through colored pluggables. Quite obviously, this solution is an intermediate solution, but enables this interoperability, this separation between the two worlds, between the optical equipment and the IP equipment. That separation is maintained. And it is also possible to have different types of clients. I can ensure certain SLAs. I can continue selling capacity and having the router network in that network. And the positive thing of this solution is that it consumes less than the traditional transponder solution, but the negative point is that I reduce the fiber capacity. Now, going back to some of the previous slides, this is something that the industry is no longer has this concern regarding so much capacity per fiber because of this availability of fiber. It is cheaper to, in this way, include several parallel fibers instead of obtaining as much as possible from just one fiber payload. These are some comparisons. We have the model network, and this analysis was done on a 1,000 kilometer network. And basically, regarding the investment, this can be reduced 24 to 41% with these transponders options. With thin layer transponders, it consumes less energy, less power, 36% less. As to the footprint, it is 50% less space. And this is quite necessary in the data centers. The smaller footprint is important in order to have more capacity and also consuming less power of power savings. And the only disadvantage that this has as regards the traditional transponder model is that it has 30% less capacity. Now, to summarize, where do I have to use what models? Where should I use a traditional transponder connected to the router in black and white when when fiber is scarce? So a provider that only has a couple of fibers will try to make the maximum gain or do the most with that fiber pair. Over long haul applications or also subsea applications where you invest hundreds of millions of dollars and maybe one company has just one or two fiber pairs and they want to make the most of that fiber pair. When there are different services that have to be supported, we speak about Ethernet services, different speeds and customers, etc., fiber channel customers. And when then there are advanced traffic functions that are required, such as grooming protection and so on. In the case of the thin transponder, the recommendation is to use this when there is a lower variety of service that have to be supported. This is supported by this technology. This is also when the space and the power are limited or when I need to consume less power and space. Also when some of the traffic functions are necessary. And that would be the case of virtualizing bandwidth, as well as when we wish to have an increased reliability of the IP traffic or the type of transport that is being done, as well as when IP and optical divisions are separate and demarcation requirements. In the case of IP over DWDM, this is when I need to do something that is very cheap, when my capex is a minimum, and only when traffic is only IP or Ethernet. This is not a solution that supports other types of traffic. And the missing point here is when these are networks that are not complex networks. I had mentioned this a while ago. This is when these networks, when these are more complex, the IP over DWDM start to fail, particularly when we want to do most and get more capacity out of that network. So that would be all. Thank you for your time. Any questions? Yes, we have time for questions. I think Thomas has a question. Name and enterprise. I'm Thomas Lynch. In one of the slides, you introduced the different transponders and the IP over DWDM. In the case of IP over DWDM, redundancy is resolved in layer 3, and in the embedded transponder it's layer 1. And in the thin transponder, you said that the thin transponder is different. How do you solve the redundancy with a ring? Or the case of a thin transponder, this is inserted in a DWDM network. There is a DWDM equipment, so the intelligence given by the protection of the classical transponder, which can be an OPS, it's like an optical switch. This is something that you also have in the thin transponder. So depending on the intelligence of the network, you can have GMPLS protections, but of optical paths, particularly for mesh networks. So this is also useful for the thin transponder. So you have those advantages. Simon, introduce yourself. Good morning. I'm Simon Perez from the Internet Society. I have a question. You introduced several products of DWDM, end-to-end, and in that product line, where do you include the interconnection of the data centers for cloud regions? For cloud regions with these data centers, all the requirements are and the tools are different compared to a normal metro network.
Actually, there are several types. Well, it all depends on. Well, if you look at what an hyperscaler does, usually in the data center, they have multiple fiber paths, over 4, absolutely independent, with independent exits, outputs, and they create point-to-point, end-to-end links. So if something clashes, then they can take the other. So there are 5 data centers that are interconnected, from 3 to 5 data centers interconnected for a cloud region. That's my understanding. Exactly. And for instance, if it is a HTC provider, an ISP, that rationale is there. The OLM machine do it. It can be either with optic protections or GMPS protection, where the traffic is rerouted, but they always have those multiple paths. Only, obviously, depending on the more fiber paths you have, the higher the capex you need. So, but you are not limited, because you can only have 2 paths of fiber. Usually the connection between the path centers, we try to have a redundancy with more than 2 paths of fiber. Thank you. A round of applause for our speaker. Good presentation. And now let me invite